The last thing that we're going to talk about in our sort of introduction to vectors in this course is an alternative formula for finding the dot product. So in the previous video, we saw how we can use the components A and B to find the dot product. So we take the sum of the product of the two horizontal components, A1 and A2, and we add the product of the vertical components, B1 and B2. Now, just like we saw that there's another way that we can describe the location of a vector, instead of using A and B, we can use its magnitude and direction angle. There's another way that we can find the dot product as well that has to do with the angle between the two vectors for which you are finding the dot product. So another way that you can find the dot product is by multiplying the magnitudes of both vectors times the cosine of the angle between them. Now, this alternative formula is a direct result from the law of cosines. Now, I worked on the proof a little bit myself so that I could maybe show it to you because I know some of you are interested in that, but the math gets a little bit more complicated than probably what we're ready for. So I'm just going to kind of show you briefly where this comes from. What does this have to do with the law of cosines? Well, if you think about our two vectors, if I have vector v and I have vector w, and then what we're looking at is the angle between them, theta. Well, if we close this off and form a triangle, you can see that what you've got there is a side angle side pattern, which is where we would want to use the law of cosines. Now, you can use the magnitude of V and the magnitude of W as those two side lengths, and then theta is the angle that's in between. So you can use the a squared plus b squared minus 2ab cosine c, which is the law of cosines, and apply it to this triangle. And what you end up with as a result is this relationship right here for your dot product. So if we then take that formula in and of itself isn't entirely helpful. It's another way to find the dot product, but the dot product on its own doesn't tell us a lot. But we can use the dot product to find the value of that angle in between. Now, it is important to note that the angle has to be non-negative. Okay, we only want the positive direction when we're measuring the angle between. If we were to take from this original formula right here and divide both sides by the product of the magnitudes, we would end up with this formula here. We would just be getting cosine by itself. If you divide by the product of the magnitude of V and the magnitude of W on both sides, then that's what you're left with. And then furthermore, if we want to find the value of theta, we need to get rid of this cosine. So we take the inverse of both sides, which gets us theta by itself. And so the formula for finding the angle between two vectors is the cosine inverse of the dot product of the two vectors divided by the product of their magnitudes. And so that comes from that alternative form of the dot product. Okay, finding out that angle can be helpful for a lot of reasons. Okay, so one of the things that you can use that angle measurement for, which I think is kind of interesting, if anyone is interested in video games at all, if you play like a first-person role-playing game where you are kind of using the eyesight as you're playing the game, it's as if you're seeing it yourself, then when you look straight ahead, you have a certain angle of vision of what you can see in front of you, kind of like your peripheral vision in that value there. So vectors are used a lot in game design, computer programming, graphic design, because they have a length and they have a direction. So it kind of is, where do you want to put it and how far away from this perspective point that you're using. So here's one vector and here's another vector, and the angle between them will show you the viewing angle that you have in a particular scene of whatever game. And so obviously that would be something that you would want to maximize as you're playing, or depending on the purpose of the game, maybe you want to minimize the angle of of sight that you have. Another way that we might want to do this is when looking at, this is going back a little bit more physicsy, but looking at torque. When you have like a bolt, okay, and let's say that I have like my socket wrench that I put over the bolt, and so we are going to crank that wrench and try to turn the bolt. So you're going to exert force in a downward motion on this, and that's going to turn the bolt. Now, the angle in between here is important. The closer you get to 90 degrees, the more torque, meaning the more turning force you're going to have on that bolt. If you push your force maybe this direction, you're not going to be able to exhibit as much force on that bolt with a turning motion, which is what torque represents. So that angle between becomes really important. Maybe you're trying to check like the functionality of a machine or an engine or the gears on your bicycle or something like that. And you want to make sure that your machine is exerting the optimum torque, which would be 90 degrees. If it's, you can do those calculations and determine if it's gotten less, if it's gotten more, which is why it's not running the most efficiently. That's where you might want to do some upgrades or things like that. So those are a couple of reasons why knowing the angle between two vectors can be really useful. So let's look at some examples here then. I'm going to leave that formula up here where we can see it. So we want to find the angle theta between the two vectors v and w, which are defined as such and shown in the image here. So there are three things that we need to know then. We need to know the dot product of v and w. We need to know the magnitude of v, and we need to know the magnitude of W. So we're going to start by finding those things. So let's start with our dot product, V dot W. And you notice when I say that out loud, I'm saying V dot W. It is not V times W. There is no such thing as a vector times another vector. You can dot two vectors, you can cross two vectors. That's not something that we're going to do in this class, but multiplying is not an operation that we have between two vectors. You can multiply by a scalar, but you cannot multiply two vectors. So V dot W is going to be 3 times negative 1 plus negative 2 times 4, which gives us negative 3 minus 8. So that is equal to negative 11. Then we need the magnitude of v. So that is the square root of a squared plus b squared. So in this case, that's 3 squared plus negative 2 squared, which is going to be the square root of 13. And we're going to leave it just like that. Don't make it a decimal, because the more times we round, the further off we are going to be, okay? A tenth of a degree doesn't seem like that big of a deal when these rays are very, very small on this graph. But again, if I change this angle just ever so slightly, like from here versus here, that's not that much of a difference right there. And that's maybe like 1 degree or less that I changed it. But you can see the further out I extend that, the further away the location of my vector is getting from where I actually want it to be. So the least amount of rounding possible is always going to be the best, because with very small numbers, it may not make a difference. But typically when you're looking at vectors, you're talking about navigation. So you're talking about like miles and hundreds of miles, or you're talking about forces which might be many, many pounds, and that's going to make a big difference. So that's why the rounding matters so much. And then the magnitude of W is going to be the square root of negative 1 squared plus 4 squared. So that is square root of 17. No rounding yet. So now we're ready to plug this all into our formula to find theta. Theta is going to be the cosine inverse. It will always be cosine because of it coming from the law of cosines. The way that the triangle was set up dictated the formula that we needed to use, which is why we chose cosine. And so this won't ever change. It's not going to be tangent. It's not going to be sine. Cosine is the only one that makes sense in this situation. So the dot product was negative 11 over the square root of 13 times the square root of 17. And you just put that all straight into your calculator and you get 137.7 degrees. Make sure you're in degree mode, and you're going to have to use some parentheses there when you type all that in. But that is what we get. That's a 7, not a 4. 137.7 degrees is that angle between those two vectors. That is probably not drawn to scale, but that appears pretty close based on what we're looking at. The last thing that we want to look at, as I mentioned before, in the application of torque, the optimum torque is going to be when the angle between the force and the wrench or the gear or whatever it might be that you're working on is 90 degrees. In terms of vectors, that is called vectors that are orthogonal, okay? Two vectors are orthogonal if the angle between them is 90 degrees. In the context of vectors, we don't use the word perpendicular. Okay, orthogonal is always the word that we're going to use in this context of vectors. And it seems weird that there's another word, but it's kind of helpful when you're working in different fields of mathematics. When you see that word orthogonal, then you know that you're working with vectors as opposed to just regular scalars. So that's one of the reasons why the word is different. So the way that we can check if two vectors are orthogonal, which like I said, one reason you might want to do that is to optimize your torque. The dot product is going to be 0 if two vectors are orthogonal. So that's a pretty easy thing to check. So for the final example here, we want to know, are these two vectors orthogonal, v and w? So what we want to do is we want to check their dot product. So we want to look at v times w, which is going to be 6 times 1 plus negative 3 times 2. And you can kind of see what's going to happen here already. 6 plus negative 6 equals 0. So that means that we can conclude that v and w are orthogonal. There's a lot of reasons why you would want that angle to be 90 degrees. And so this is an easy way to check pretty quickly to see if that is actually the case. If it was anything other than the number 0, then they are not going to be orthogonal and that angle is not going to be 90 degrees. All right. So that is the end of what we are going to look at in this course with vectors. If this is interesting to you at all, then definitely think about taking physics, definitely think about taking calculus. These are all going to be places where sort of this understanding of vectors gets to be expanded a little bit. They play a big role in technology. They obviously play a big role in mechanics and things like that, engineering. So this is just a little taste that you get, and then you can dive into this a little bit deeper in some of your other classes. So that is it for this unit, guys. I'll see you later.